Okay, so now we're going to talk about reactions that occur in the gas phase. And so in order to do these, this is also going to be using our balanced chemical equations. But in addition, we're going to be using the ideal gas law, PV equals nRT. And in particular, notice that N is a variable here. Remember, N stands for the number of moles of gas. Right, so that's how we can use our balanced chemical equation. Remember, in order to use a balanced chemical equation, we have to have moles, but we can use our ideal gas law and solve for moles or plug the moles in, right? So this variable of moles is going to be really important. So we're going to take a look at this reaction here. We have our solid sodium, what's called sodium azide, gets converted to solid sodium and nitrogen gas. This is actually the reaction that happens within an airbag to expand the airbag really quickly, right? Converting a solid to a gas. Typical airbag has 50 grams of this sodium azide. So what we're going to do is determine the volume of nitrogen gas that would be generated by the decomposition of 50 grams of sodium azide at 85 degrees Celsius and 1 ATM, right? So step one is we're going to have to get the theoretical yield of our nitrogen gas. And we want to plug it in, eventually plug it in to our ideal gas law, PV equals nRT, because it wants to know what the volume of nitrogen gas is, right? So we're going to use our balanced chemical equation to figure out moles of nitrogen gas, and then we can get the volume of nitrogen gas because we have our other variables. The pressure is given, the temperature is given, and R we always know from our constants page, right? So we'll have to use the value for R from our constants page, okay? So two steps. First, figure out number of moles. So first we got to use this variable here, moles of our gas that's produced. So we're starting out with 50 grams of the sodium azide. In order to use our balanced chemical equation, what are we going to have to do? Get to moles, which means that we're going to need the molar mass of the sodium azide, which again, you should be able to calculate from the periodic table, but I will, for the sake of time, give it to you. Okay, so then I'm going to get from grams to moles by using this molar mass, 0.00999 grams of sodium azide per 1 mole of sodium azide. Now I can use my balanced chemical equation, which tells me that if 2 moles of sodium azide are consumed, I will produce 3 moles of nitrogen gas. Okay, and I actually want to stop here. I don't want to calculate grams of nitrogen gas because I'm trying to plug it in to the ideal gas law. And that variable there is for moles, not for grams. So I'm going to stop here and punch this into my calculator. And I would get 1.15366 mole, well, I guess I can verify here, make sure my units are correct. Grams of sodium azide cancel. Moles of sodium azide cancel, so I'm indeed left with moles of nitrogen gas. And then, of course, sig figs, because this is a chemistry class, we always got to pay attention to sig figs. I would have 2 sig figs in my initial measurement, so I'm going to have to mark my second sig fig. Since I'm going on to do another calculation, I'm not going to round, right? We will only round at the very end of the problem. I'm going to use this whole number with all those digits in my next calculation. I'm just going to keep that sig fig marked. So now I need to use PV equals nRT in order to solve for the volume of gas. If I divide both sides by the P, I can move it over. So volume equals N, which is my number of moles that I have here. Okay, so N times R, I'm going to have to go to my constants page. and the R is 0.082058 liters ATM per mole Kelvin. And again, I'm copying all those digits. I know it's a pain in the butt, but chemists love our digits. So we're going to keep everything that we can. And this is AT, and then paying attention to the units as well, because we'll see that they'll all cancel out nicely, just like they did when we were doing our ideal gas problems. Liter ATM per mole Kelvin. So liter ATM per mole Kelvin. Now times the temperature. The temperature is given as 85 degrees Celsius. But remember, in order to use the ideal gas law, I need to convert that temperature to Kelvin. And being really good about copying down the units of R are a good warning sign to make so that I don't make that mistake. I need Kelvin in order for that to cancel. So on my constants page as well, it says that I can get to Kelvin by taking that degrees Celsius and adding 273.15, okay? So that would take me to 358.15 degrees. Whoops, not Kelvin, or not Celsius, Kelvin. That's what I wanted. All right, and if I was being really good, I'd keep my sig fig here marked as well, because this is an addition problem and I have it in the 10th place for my initial measurement. And then I'm going to divide by the pressure, which is 1.00 ATM. Okay, so punching this into my calculator, I'll get my numerical answer. Let me move it up so I got a little bit of room to write. I'll get my numerical answer, which is 33.905. All right. Now I'm going to pay attention to units. The moles will cancel out. The Kelvin will cancel out, and the ATM will cancel out. And so I'm left with units of volume, which is liters. That's awesome. Now I need to pay attention to sig figs. For my moles of sodium, for my moles of nitrogen, I have 2 sig figs. I have 4 for my temperature measurement, and I have 3 for my pressure measurement. So then how many will be in my final answer? I'll have to round it to 2 sig figs, right? Whichever one is fewer. So 34 liters of nitrogen gas in a typical airbag. Okay, so again, notice how we're playing the very same stoichiometry game that we were doing before, but now we're taking that information of moles of product, of gaseous product, or even gaseous reactant, and using that in our ideal gas law. Remember, with the ideal gas law, everything has to be, temperature has to be in Kelvin. Okay. The other thing about the ideal gas law that's kind of interesting, a consequence of the ideal gas law, is given that a reaction will take place kind of like at a given temperature and at a given pressure, the mole ratio that you get from a balanced chemical equation is going to be equivalent to the volume ratio as well. So this balanced chemical equation telling me that I need 2 moles of carbon monoxide per mole of oxygen, that's the same thing as saying that I need 2 liters of carbon monoxide per liter of oxygen, or even 2 milliliters of carbon monoxide per milliliter of oxygen, right? A consequence of the ideal gas law, maybe we didn't point it out, but that's kind of interesting, is that all gases are treated the same, right? So it doesn't matter what the identity of the gas is, it just matters how much of it you have in terms of moles. That will directly correspond to the volume at a given temperature and pressure. Okay, so kind of to picture it here, we talked about moles, as our quantity. We need to get to moles to do our balanced chemical equation. But if we're talking about ideal gases, it's equivalent to talk in terms of moles or in terms of volume. Either one will work because those ratios are going to be locked in. So if it's a 3-to-1 molar ratio, it will be a 3-to-1 volume ratio as well. Okay. All right, so another gaseous problem here. Sodium peroxide is used to remove carbon dioxide and to add oxygen in spacecrafts. It works by reacting with CO2 to produce sodium carbonate and oxygen. What volume in liters of carbon dioxide at STP will react with 1.0 kilograms of sodium peroxide? And so the balanced chemical equation is given here. And we are given our starting value of sodium peroxide, and what we want is the volume of CO2 that's going to react along with it. And it says STP, that's standard temperature and pressure. Standard temperature and pressure is 1 atm and 0 degrees Celsius exactly. Really, when we say STP, we mean exactly 1 atm and exactly 0 degrees Celsius. What we really mean is we're not going to let that limit our sig figs. Okay, so now I'm going to start out with the quantity that's given, which is the 1.0 kilograms of sodium peroxide. And I'm going to have to count, so this is STP. In order to use my balanced chemical equation, I want to get to moles. So I'm going to have to use the molar mass of sodium peroxide, which I'll again tell you, but we should be able to get it from the periodic table, is 77.978334 grams per mole. So in order to convert to moles, I'm going to use this molar mass. And convert to 1 mole sodium peroxide. Now I can use my balanced chemical equation, which tells me that 2 moles of sodium peroxide are consumed along with 2 moles of CO2. And since eventually I want to use my ideal gas law, PV equals nRT, I'm going to leave it in moles. All right, so I'm going to solve for it as getting my answer in moles. So punching that into the calculator, 12.82407, going to pay attention to my units. Oh, snap. I messed something up here. We need to include something. Actually, I did it in my calculator, but I didn't do it here. I need to first jump from kilograms to grams. I got to convert the fact that 1 kilogram is equal to 1,000 grams. Otherwise, kilograms and grams wouldn't cancel out. All right, so I was just testing to see who was paying attention. No, that was my bad. Okay, so anyways, punch that all into your calculator. Now you'll get 12.82407. Going back and paying attention to units. So notice how I messed it up. And then when I went and did my unit check step, that's when I discovered my problem. That's why being so good about writing your units is really important. Exactly that kind of situation where I was able to catch a mistake before it was really problematic. Kilograms cancel, grams will cancel. Now moles of sodium peroxide will cancel, and I'll be left with moles of CO2. Okay, I have, paying attention to sig figs, I have 2 sig figs in this. This is exact, because I get it from my metric prefix conversion sheet. This mole ratio is exact, and this molar mass has a ton of sig figs. So I'm going to have 2 sig figs in my answer. But again, since I'm going to move on and do another calculation, I'm going to keep all those digits and just mark my sig fig. All right, and I'm trying to solve for volume. So I'm going to isolate volume all by itself by dividing both sides by P. So now I have the volume equals the number of moles. So that's this one here. With my sig fig marked. So this is moles of gas times R, which again I get from my constants page. 82058. And this is going to be ATM liters per mole Kelvin. And since I'm really good at my units, I've reminded myself that I need to make sure to have my temperature in Kelvin. 0 degrees Celsius would correspond to 273.15 Kelvin. I'm going to take that and divide by the pressure, which was 1 ATM. Okay, so punch this all into my calculator and I would get 287.44. Being good about my units, I'm going to go back and check that moles cancel, Kelvin cancels, ATM cancels, and I'm left with liters of CO2. And I should have 2 sig figs in my final answer because my number of moles is limited to 2 sig figs. So 290 liters of carbon dioxide would be consumed along with a kilogram of sodium peroxide.